Welcome in our mathematics class, and today we are going to look at applying algebra. Take note that we've come all the way looking at how algebraic expressions are handled, expanding them, factorizing them. Now we want to look at how are they applied. Algebraic skills here, or skills of algebra, can be applied in so many situations, which some of them are mathematics parts, others are in other fields like the engineering, the science, the economics. All that algebra is applied in different perspectives. I want us to look at a situation here of three boys who chose to go for a ride. And these ones, we have Alvin, we have Bryson, and we have Calvin. Now, these three boys went for a ride. Alvin can pay $50. He can pay $50 and goes Alvin can pay $50 and goes for a ride all day without any additional payment. Bryson pays $20 to enter, and then so the second Bryson pays $20 and to enter and $2 per ride. This $20 is to simply enter. Then the last one here, Kelvin, he doesn't pay anything, no entry fee. But he pays 5 shillings. But he pays $5 per ride. Now, when you look here, you'll notice that all of them will go into the park, enjoy the ride, walk back home. They are all happy. But the question now here is, who pays the least and who pays expensive? All these boys will go home happily because this one says, I only paid $50 and I had a ride the whole day. This one paid $20 and was given 2 shillings per ride, and I think he also enjoyed. This one just entered freely, and every ride he was making, he was paying $5. So here, this is part of applying algebra. And you'll notice this. This one, if we were to show how much the total number of rides he'll go for, you'll find that irrespective of all the rides he goes for, total paid is what? $50. For this one here, he'll pay a standing entry charge of $20 plus 2 shillings per ride. Let me call it 2R, depending on the number of the rides. You see, this is already algebra. And the last one, entry is free but pays a total of $5 per ride. So if he goes for 50 rides, he'll pay a total of $250, sorry, a total of $25. So keeps on changing, but you'll realize that all these boys walked home happily, that they have gone to the park and they have had a ride and they've come back home. So in algebra, besides such kind of application, different situations can be modeled with algebraic expressions. It is not specific that it must be particular situation. No, the situation keeps varying, and different situations can always be modeled with algebraic expressions. And to apply the rule here, we find that the variables must be clearly defined. Then the values are substituted for the variables. For example, from what we've just seen about the boys above there, we had Bryson, who was paying entry fee of $20 and was paying a total of $2 per ride. So we need to identify the variables. For this case, we can say that let every ride be actually denoted by X. Or let us give it a small r. We denote a ride to be r. Then in this case, the total cost that Bryson will spend will be fixed entry fee of $20 plus $2 per ride, and multiplied by r to get the total number of rides that he went for. So this one gives us an expression that shows us the total expenditure by Bryson. So we are saying here, you define the variable. First, you have to be having clear definition of these variables, and your variable here is r. If I may ask you now for this time, what does r stand for? You'll tell me r stands for a ride, right? So this is a variable and it is clearly defined. So if someone says that Bryson went there and actually had about 10 rides, then we shall substitute and say the total amount spent is 20 plus 2 times the number of rides, which is 10. This one gives us 20 plus 20, which is $40. You see that? So the number of rides must be clearly defined, just the way we've seen here. So let us look at examples and some workable exercises. Let us look at every expression at a time. We want to see how we shall apply algebra given that the total cost of K bottles, if each bottle costs costs $4. So for this case, we find that the number of bottles is K, and each bottle will cost number of dollars, which is 4. So it implies that K times 4 gives us the total cost, which is 4K. So you've been able to identify that K stands for the number of bottles. 4 is simply the cost per bottle. So if you buy K number of bottles, then what you'll have here is simply the number of bottles, the total cost for the number of bottles that you bought, which is K. Another statement we give an expression for the area of a rectangle if its breadth is 2 centimeters more than its length and the length is x centimeters. Now, if the length is x, we normally say the area is length times breadth. That's the formula for the rectangle. And we've been told the length is x, so area here is simply x multiplied by breadth, and breadth we've been told it is simply 2 centimeters more than its length. So this is x plus 2. This one will give us the area as x into x plus 2. Now, we are allowed to handle it either side. You can leave it there or you can expand it. If you choose to expand it using distributive law, it will be x squared plus 2x. And this is square centimeters. So the expression to show the area of a rectangle whose breadth is 2 centimeters more than its length and the length measures x centimeters. We need to find the expression for the total cost of hiring a plumber for n hours if he charges a call-out fee of $40 and $70 per hour. Those who have interacted with the plumbers, when you call them, you must first give them a call-out fee. That's why we have a fixed charge of $40. And then the number of hours the plumber will stay in your house making repairs, you'll be spending, it will be costing the caller $70 per hour. So what would be our total charge in case this plumber comes and stays any number of hours? So we already have the variable defined, that we have a variable called n, and n stands for the hours. So what we have here is to find an expression that will just generalize all that cost. So the call-out fee is fixed, so that one will remain as 40, and then we shall add what he will spend for every hour, which is strictly 70 times the number of hours. So this is an expression that gives us the total cost that we shall pay a plumber if he works for n number of hours. So that is it about the application. But we can also apply algebra in other areas. We have already been dealing with them, only that we did look at it as an application. But I want you to look at it from this point of view, where we have the area, finding the area of rectangle or the perimeter of a shape. Still, that one is an area where we apply algebra. It is used by survey and others. So I want us to look at the following figures or shapes, and then we see how algebra can also be applied when it comes to shapes. If you have asked your friend what type of a triangle is this, he or she must have told you that this is an isosceles triangle because it has got two sides equal, and base angles are expected to be equal because of the two sides that are equal. And then if this is an isosceles, then we want to find out it's measuring x by x and then by y. So the question that comes is write an expression for the perimeter of the above triangle. We know that the perimeter, let me call it P, is equals to x plus y, which comes to be 2x plus y. That is the expression for the perimeter. That is the expression for the perimeter. Now supposing we have been assigned some values of x and the values of y, as you can see, find the perimeter given that x is 3 and y is 2. So from this, we want to look at it. Find the perimeter given that x is equals to 3 and y is equals to 2. Take note that the perimeter is simply given by p is equals to 2x plus y. P is equals to 2x plus y. As we saw earlier in algebra, given the values for the variables, we should substitute accordingly. So we need to have, in our expression where we have x, we shall put a 3, and where we have y, we shall put a 2. So from this, p is equals to 2x plus y, that's what we have. Then where we have x, we shall put a 3, so this will be p is equals to 2 times 3, and then plus y, which is 2. 2 times 3 is 6, so p is equals to 6, plus 2, p is equals to 8 centimeters. So our perimeter can now be found as 8 centimeters. Another application, we can look at it from the finding the area of a rectangle. So we are asked to write an expression for the total area of the shape shown. The shape shown here, this is a rectangle. We can look at it measuring 3, and the other side is x plus 2. Area, if we can work out the area, let me call the area A. Area A is found by simply the length times the breadth. And area here is equal to the length, which is 3, times the breadth, which is x plus what? Plus 2. This is the same as 3 into x plus 2. Using distributive law, we can now expand this, and you'll get our area being 3x plus 6. That is an expression that gives us the area of that particular shape that we have. So now from here, we can move ahead and add another question. If x is equals to 9, then the question that is coming in, what is the area? Given that x is equals to 9, what is the area? So we add that question here. So we cannot get the area if we don't have an expression. So have we created an expression for this particular shape of finding the area? If yes, fine, we look at the expression that we have and see what is the value if at all we substitute where we have x with 9. So let us go to the expression, and then we start from there and substitute the value of x with 9 and see what will be the value of the area. So we have the expression here, a is equals to 3x plus 6. A is 3x plus 6. If a is 3x plus 6, that is what we have. But x is 9, so we substitute, you'll find that a is equals to 3 into 9 plus what? Plus 6. 3 times 9 is 27. So this area becomes 27 plus 6, and 27 plus 6 will give us 33. So the area here is 33 square units. 33 square units. So we've been able to get the area by first looking at the expression that was going to give us the total area, and then we have substituted the value of x, where x is 9, and we have our area. Take note that this expression will always work as long as we have the value of x. If we change the value of x to be a different reading, it will also change. That's why we say you substitute the values of the variables that you have identified and been given. So that is it about applying algebra. You'll meet other areas that we apply algebra. In real life situation, we also apply algebra. If you are looking at, maybe we can talk about consumption, what the vehicle consumes per liter while it is, one is driving to a place. You can also bring in algebra through that. There are many areas, as we had said earlier on. But that is it about applying algebra. Now, I want us to shift our attention and look at a new area about indices, and this is index law for multiplication and division. So, index law for multiplication and division. Now, let us recall what we know, and you'll find that we already know what index is. Only now it is about labeling or naming that now this is what we used to call, maybe the power is what you're going to call the index. We all know that that is called x squared or x power 2. It also means that it's x times what? X times x. If we have it x to the power of 3, this is x times what? X. So when you have a number or simply a pronumeral raised to a power of a certain number, it's equivalent to multiplying the same if it is power 3, we multiply it by itself 3 times. It's power 2, we multiply by itself 2 times. So I want us to understand that if we have a number like 3 raised to power 5, it is the same as, say, 3 multiplied by 3, multiplied by 3, multiplied by 3, multiplied by 3. How many times? 5 times. Now, here, this one here is called a base. This one here, 3 is raised to 5. That raising, this one is called index. Or exponent. It is called index or exponent, what we have up there. So 3 raised to 5, 3 is the base, 5 is the exponent, or also called the index. This is what indices are. So if you don't want to write a number repeating itself so many times, you just relax and say that number raised to the number of times. If you have a number like 2 times 2 times 2, don't waste space writing all that. Just write this is the same as 2 raised to power 3. The base is 2, the index is 3. Now, what happens when we are multiplying? Look at this. Now that we know what an index is or an exponent is, we know what our base is. Supposing we have three raised to the power of 5 multiplied by 3 raised to the power of 2. It's something you write until you reach an extent that you are also wondering where are you. Because this is 3 multiplied by itself 5 times. So we shall have 3 times 3 times 3 times 3 times 3. We have that. This is equivalent to 3 raised to the power of 5 and then multiply by 3 raised to power 2. So what will be our answer? Look here. We only, if at all we said, if it is raised to power 2, it's twice. Raised to power 5, we said 1, 2, 3, 4, 5. So if we want to find the solution for this, we just count the number of times 3 has appeared. 1, 2, 3, 4, 5, 6, 7. So which implies that 3 raised to power 5 times 3 raised to power 2 should give us 3 raised to power 7. So what you notice here is something. Look at this. This was 5. This was 2. The solution here is reading 7 after all that. Which means if you had the knowledge earlier on, you don't need to count all these 3's. Just take the powers and add them together. We shall look at that. And then let us look at the division. This is about multiplication of simply the indices. Supposing you had 2 raised to 6 divided by 2 raised to 5. Now, we would do it in a very local way because we don't know what exactly are they trying to look for. So, we take this 2 raised to power 6, we multiply it how many times? 6 times. Divide is a quotient, it means over. So we can write it like fraction. So over 2 raised to power 5. This is 2. 1, 2, 3, 4, 5. In fractions, we say that those factors which are common in both numerator and denominator are always cancelled. So we are going to cancel here. 2 and 2, 2 and 2, 2 and 2, 2 and 2. And 2. Oh, we are done, but we are remaining with one numerator of 2. So which gives us here 2 over 1, which is equals to 2. Take note, 2 is the same as 2 multiplied by itself how many times? 1 time, which means it is the same as 2 raised to the power of 1. That is what we have here. When you come here, you will see some relationship. When you are dividing powers, supposing you subtracted the powers 6 minus 5, would you get 2 power 1? That is what we are going to look at. So in general, let us take note of the following and understand how index notation operates. We've already known that if we have a number like this, n stands for the exponent or the index, while 5 stands for the base. And this one simply means 5 will appear or will multiply by itself how many times? N number of times. It is also possible that we look at a number raised to the power and we get the solution. If you are given 2 raised to power 5, what is the value? Because you'll have this one as 2 times 2 times 2 times 2, 5 times. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. Which implies that 2 raised to power 5 is the same as 32. So you can be able to move from that index notation straight to this one we call it the decimal notation or the numeral that we have. Another point to note. We have different bases. 4 multiplied by 5 raised to the power of 3. This one is index notation. Its expanded form would be 4 multiplied by 5, then by 5, then by 5. How many times? 5 3 times, but 4 only 1 time. This one is called the expanded form. It is the expanded form of this notation of 4 multiplied by 5 raised to the power of 3. Now let us look at the index law of multiplying and index law of dividing. We have already seen it, but we want to clarify and put it clear that when you have a number like 3 raised to m multiplied by 3 raised to n, 3 raised to m multiplied by 3 raised to n, the law of index, that is the law of index about multiplying, will mean that when you have this, it is the same as just having the base written and then the powers put together by the sum. When you multiply two numbers with the same bases, it is the same as adding the powers and maintaining the base. So this one is what you'll have. Take note that m plus n is not the same as mn. It will remain m plus n. So this is what it means there. If we use an example, let us take a number like 7 raised to 2 multiplied by 7 raised to 5. Can you look at that? From this rule, our solution should be the same as 7 raised to 2 plus 5. 2 was a power, 5 was a power. So we add these because they are numeral numbers. We can add them together. You find our answer to be 7 raised to the power of 7. That is the law of multiplication concerning indices. For the division, the law of index about dividing is simply, again, going to base on similar way, but the powers will be different. Take, for example, 3 power m divided by 3 power n. From what we have seen earlier, the law of division about index, this one will be the same as 3 raised to m minus n. Can you confirm if it's the correct thing? 2 raised to 4 divided by 2 raised to 2. From this, it means the answer should be 2 raised to 4 minus 2. Is it true? Which will give us 2 raised to 2, which is the same as what? 2 times 2. This is the expanded form. This is the index notation. Now, let us confirm this by applying what it is. 2 power 4 is the same as 2 times 2 times 2 times 2. Division means over. This is 2 times 2. So we can simplify here. 2 and 2 goes, 2 and 2 goes. We are remaining with 2 times 2. 2 times 2 is the same as 2 power 2, which we have here, or 2 times 2, which we already have there, which is the value of 4. So we can prove that given 3m divided by 3n power n, the answer is 3 the power m minus n. That is what we get. So let us now get to the exercises and see how indices and index notation and actually division and multiplication of index can help us. Simplify the following using index law of multiplication. Simplify the following using the index law of multiplication. So the first one is 5 power 3 times 5 power 7 times 5 power 2. So this one will be the same as 5. Up here, we have the powers, which will be 3 plus 7 plus 3. It will be 3 plus 7 plus 3. That is what it will be. So, when you combine what you find, it is 5 raised to the power of 13. That will be our answer, 5 raised to the power of 13. Take note, the base remained, but we added the powers. For the second one, we have 2, so we maintain the base because the base is the same. The powers, we have 3 and 4, so we add them. 3 plus 4, this one gives us what? 5 to the power of 7. 5 to the power of 7, because we are adding the powers. The last one, we have 3 terms, and each one is, we have the base sharing the same, so 5. Then the powers we add, this is 5 plus. When we only have a 6, it means there is something. It is 6 multiplied by only itself, only 1. So it's the same as power 1. So we shall have 1 here, and then add 6 power 3, then we have 3 here. This one gives us 6 to the power of 9. 6 to the power of 9. So this is about the law of index when we are multiplying index notation. How about when we are dividing? How do we approach it when we are dividing? Now, here we go. 5 raised to 7 divided by 5 raised to 3. This is the same as, the base is 5, as you can all see. The power is 7, another power is 3, which means we shall subtract the powers. This is 7 minus 3. It will give us the final solution as 5 raised to 7 minus 3 is what? Is 4. That one will be like that. For the second one here is 6 raised to the power of 20 divided by 6 raised to the power of 5. As long as the base is the same, then it is easier to deal with that. Then we take the power of the first one minus the power of the second one. This is 5, which will give us 6 raised to the power of what? 15. Now for the last one here, this one we need to be keen about it, because we can move ahead and simplify further and see what exactly you're doing. Now, check this out. This is 4, this is 10. What is the common factor between 4 and 10? It's 2. So by 2 is 2, by 2 is 5. So having done that, then we have 5 times 5 power 6. 5 times 5 power 6 divided by 2 times 5 power 2. That is what we have. This is, the base is 5, the power is 1. The base is 5, the power is what? 6. So the numerator can be put together to form 5 raised to the power of 1 plus 6, which gives us a total of 7. And then the denominator remains 2, because 2, the base for 2 is not the same as the base for 5. So we shall just continue and look at it, times 5 raised to the power of 2. Now, then from here, we combine. This will be 5 to the power of 7 divided by 2 times 5 to the power of 2. The base here is 5. The base up there is what? 5. So this one can be used, when we can be applied using the law of division, which will give us 7 minus 2 over 2. So 5 raised to 7 minus 2 will give us 5 raised to power 5. And then down we are remaining with only 2. So this one will become 5 power 5 over 2. 5 raised to power 5 divided by 2. That is what we get when we are dividing. Now, in most cases, we have dealt with only numerical what? Bases. But we have got a situation where our bases are non-numerical and they are still having the powers or the index or exponentials. Are we supposed to be able to handle that, or that is a different situation? Let us look at how to simplify larger expressions with non-numerical bases. Those expressions whose bases are not numerals. I'll take the simple one and then you see how to approach it. Numerals, in fact, and all of it is just a. We can bring it easy together and then we wind up easily. Now, a power 2 times a power 3 times a power 5 divided by a power 1 times a power 3. What is the base? For the numerator, the base is what? A. For the denominator, the base is also a. But what are the indexes or the exponential for a? Because it's a multiplication here, so it is a to the power of, add the powers, 2 plus 3 plus 5. And the denominator is 1 plus 4. That is 1 plus 3, sorry. 1 plus 3. So this is the same way we are applying those numbers, which those which had numerals as their bases. But we can also do the same on this. And then you get, when you do this a, you'll find that this is the same as 5 plus 5. So this is a power 10 over a power 4. The law of division when dealing with index says if the base is the same, we should do what? We should subtract the power. So this is the same as a 10 minus 4, which is a power 6. Take note the base are non-numerical. They are non-numerical. So I'm bringing another complex one now, of which we shall now handle it with a bit of applying what we've learned in the past. Simplify simplify 10 raised to the power 10 times x power 3 times y power 4, or 10x power 3 y power 5 divided by 1 divided by minus 10x4 y 3. If you can recall when you are dealing with algebraic fractions, what happens when you are dividing fractions? We said when dividing fractions, it is the same as multiplying by its reciprocal. And what is this that we are calling a reciprocal? A reciprocal is one that you invert. The numerator becomes the denominator, and the denominator comes up to form the numerator. That is what a reciprocal is. So for this case here, we need to change this and say multiply it by what? Its reciprocal. And if we have to do that, then it will follow that this will be rewritten as 10 a number raised to divide by 1 is just the same number. So having reached here, we now look at what can we bring together, what can we multiply, what can we be able to multiply. Now 10 times minus 10, A positive and a negative is always a negative. So this one will give us minus 100. Then x power 3 times x power 4 is x power 3 plus 4. Then y power 5 times y power 3 we shall add. Before I finish that, someone will think that because this was the denominator, you start subtracting. No. The rule here forbids us to do that. Because the moment you multiply by the reciprocal, things changes. Right? So this is what we have. X power 3 plus x power 4 and y power 5 plus what? Plus y power 3. So you can simply now conclude and find that our answer is minus 100 x is power what? X is power 7 and y is power 8. X7, y8. That is what we can be able to get. So it doesn't matter whether you are dealing with the numerals or you are dealing with a non-numeral basis, but we should always be able to calculate and find how the law of both division and the law of multiplication when it comes to the index is simply applied. So let us look at one last, and then we stop. Simplify. Now we have a mixture of numerals and we also have the bases. But the main interest that we have is to work out this. What we said earlier on is that when multiplying fractions, numerators go by themselves and the denominators also are multiplied by themselves. So what are we supposed to do in such a case? Now here, it's because it's multiplication. Take note that anywhere we have common factors between the top and the numerator and the denominator, we shall always do what? Cancel. So I want to have this one will be like 5 power 3 multiplied by 2 power 4 divided by 2 power 2 x5 times 5 power 2 x. Now, if you are very keen, 5 power 3 is up here, but there is 5 power 2 down here. So there is nothing wrong if you say, this is, if you solve this by saying this is the same as 5 power 3 minus what? 2. You'll be done with this. Then we have 2 here, 2 power 4 and 2 power 2. This means this is 2 power 4 minus power 2. So we shall be done with this and that. What remains at the bottom here are only for the pronumerals, that is the x and the unknowns, the x and the x. This is x power 5, this is x power 1. We are multiplying. So this x power 5 times x power 1 is the same as x power 5 plus 1, which is what? 6. Already we shall be done with that. If you want to go the longer way, you can break it and start cancelling one by one. But because we have the powers, I'll introduce those powers and we shall see it. So for 5, this 5 will be 3 minus 2. So we are done with this. Times 2 is power 4 minus 2 power 2. And then the denominator, so we are done with this, we are done with that. The denominator remains is x power 5 plus power 1. There we are. So this one will give us what? 5 power 1 times 2 power 2 divided by x power 6. This will be our answer. 5 power 1, which is just 5, times 2 minus 2 is 2, so 2 power 2 divided by the product of x5 and x1 is x power 6. That is how we handle algebraic, the index when you have algebra and we have a mixture of numeric bases and they have the indexes. This is how we should be able to handle it. I believe when you come across questions touching on index notation, you'll be able to handle it. That is it for now. When we come back in our next class, we shall be looking at the zero index and power of a power. Thank you.